Sometimes adding new features to our data will increase the performance of our machine learning model. The example we saw earlier, we try to separate our two classes, the blue and the red, but since their feature values came from the same distribution, we understood that using any classifier is going to do a poor job. It's not going to be able to separate these two classes. We didn't even bother training a classifier for the task at hand. We plotted the data, and we were able to visualize, you know what, there's no way, there is no pattern, there is no structure here for a model to exploit. Let's go back and revisit that case, but let's generate these x1 values, one of the feature values, using two different distributions. One class is going to generate their x value from one of the distributions in blue, and let's say the red one's going to generate its x1 values with this orange distribution shown here. Now we see some overlap with these two distributions, but that overlap is minimal. Yes, there is some overlap, but they're not completely overlapped. There is some separation. Enough separation that we believe, just by looking at here, that we can do a pretty good job to train a classifier to separate our two classes. Yes, it's not going to be perfect, but it should be just good enough. Now what happens if we add an additional feature, x2? And these x2 values for the features also come from two distinct distributions. Yes, there's overlap, but let's see how it's going to perform by having x1 and x2 with our observations. So two features for our observations. Let's go ahead and plot the data. So we have the plot of the data, and as we saw before, it's reasonable to assume that we can draw a classifier, even a linear classifier, to separate these two classes. Yes, we won't be perfect, but it's going to do a better job than before. So this is the combination of x1 and x2. Let's go ahead and use logistic regression, but let's go ahead and do it twice. Once it's only going to use one feature, and a second time where it's going to use both features, x1 and x2. So do a train test split. Let's import our logistic regression. Remember, logistic regression is a classifier, a linear classifier. So we see here, we can sort of anticipate where it should draw the line. Now, if we have two features to work with, we have more degrees of freedom, and it's probably would draw a line perhaps along this diagonal right here. If it only had one feature, it probably would just draw the cutoff point perhaps somewhere around right here. Remember, it only has one feature. If we train it with one feature, it can only draw sort of a cut along this dimension. But if it has two features, then it can do a diagonal and do a better job that at least we see right now initially. So let's go ahead and confirm our initial expectations. Let's train our models. Let's go ahead and print out the accuracy for both of them on the test set. And we see indeed when we have two features, we do a better job to classify our observations. Since we only have two dimensions, we should be able to easily visualize the decision boundary. So we'll do that with this block of code here. So this decision boundary tells you in the space what would have predicted, what would our model have predicted. So the regions in blue, if we had an observation here, the classifier will predict blue. If it's in the red regions, if an observation is in this red zone, it will go ahead and predict that observation to be red. So this is our decision boundary. Notice we use a line since we're using logistic regression, it's a linear classifier. So this is when we use two features, but here this dashed line represents if we only had used one feature, so this confirms our initial guess how these classifiers would work. So it seems that using two features in a situation will do a better job. But what happens if we had a lot of features? More than two. We increase the number of features in our data set. At some point we have a very high dimensional space. And these points will be too spread out apart. And because of that, it's going to be very difficult for our model to learn from all these observations. We may not have enough observations given the number of dimensions we have in our data set. This is the idea of a curse of dimensionality. As we increase the number of features, in generally will require more observations for our model to learn from. There's more combinations that can happen in this higher dimensional space, so we need more training examples. We may not have enough training examples for what we're trying to do. Of course, it's easier said than done to collect more data, but sometimes we may want to clamp down on the number of features given the fact that we cannot collect more data. So let's go back to the California housing data. So we should now be all familiar with this data set. So you can import it. Let's go ahead and train a random forest regressor, decision tree regressor. And with some of these models, we can generate feature importance. We saw that with linear regression. We can do that with decision trees. We'll talk more about that with decision trees, but there is an attribute of a trained model called feature importance that's going to devise a metric of how important was those features. This might be nice to know because we want to know, okay, which feature really helped out to make the prediction. And we can use that information because that might suggest we should pay more attention when we collect values for that feature in future data collection process. Or perhaps realize, you know what, these features aren't important, why are we recording these values? Maybe it's very expensive to collect data, and it would be cheaper if we just collect less characteristics, less attributes of our data set. So we're going to use a randomized search CV, so it's going to behave a lot like grid search, but it's going to randomly sample the resulting grid it generates via param grid. So we're going to explore max step min sample split. I'm going to set the verbosity to 1 so we can see a printout of how things are going. Go ahead and fit that. And notice what we're going to do here, we're going to look at the feature importance of our model. Remember, once we do randomized search or grid search, if we want the best estimator, there's an attribute called best estimator. So we'll make use of that such that we can access this attribute here called feature importance. So let's go ahead and package that all together. It's going to run this. It'll take a while. I believe it will take a minute. That's why it's important to set verbosity to 1 so we can see a printout of what's going on. Notice here for max step, we're going to sample from a binomial distribution. I want to point that out. Other thing I want to point out here is train test split automatically shuffles the data, so there's no need to manually shuffle the data prior to using train test split. Okay, so we finished running. We had an R-squared value of 0.67. And since we're examining the feature importance, we see here that the most important feature was the median income of the census block, which makes sense. I believe when we explored this data set initially, we're plotting the median home price with all these different features. This is one of the features, characteristics, categories that we saw that had the greatest correlation, the greatest trend, the greatest pattern, the greatest behavior that we just expect any model can exploit. And it makes sense also intuitively we understand that the more money people make, then the more likely they're going to have a more expensive house. Okay, so that's one way we can generate feature importance via our decision tree model. But remember when we talked about linear regression? Remember how we can generate a metric for feature importance? What do we do there when we're working with linear regression? What was that technique that we used? Well, for linear regression, we can look at the beta coefficients for each feature. We can examine them, and that's going to give us a relative idea of how important is that feature. How much of an impact does that feature contribute to the predictive value? Remember, we have a linear framework, y equals beta naught plus beta 1 times x of 1 plus beta 2 times x of 2 and so forth. So that beta coefficient tells you how much contribution that feature gives to the value you're trying to predict. The value that comes out when you invoke the predict method. And of course, in order for us to better compare these beta coefficients, we need to scale our data to have the same scale. So we use the standard scaler here, and we'll examine the coefficients, and they're stored in the coef attribute of our linear regression model. We want to make sure we take the absolute value because we're concerned not about whether we want to make sure we measure the magnitude. So we don't care if it's very great in positive direction or very large in negative direction. We care about the magnitude of our beta coefficients. We're going to scale them all, so that's what we divide by the sum, such that when you sum up all the beta coefficients, all these scores, they're going to be a value of 1. So this is our way we can generate feature importance using a linear regression model. Let's see the results here. So we also see that the median income had the largest beta coefficient relative to the rest. Also want to point out here is the R-squared value isn't so great, which makes sense because we have a simpler model. Now let's say we want to do some sort of feature selection. Perhaps we only want to include a subset of the features of our original features. So this will help out with the curse of dimensionality, but also help out for other reasons as well. Perhaps you have a very complicated data set. And by complicated I mean there's a lot of observations, but a lot of features, a lot of characteristics, attributes for those observations. And let's say you have 1,000. And if you want to collect more data, and you want to use a model that was trained with this data set with 1,000 features, then that means that when you go collect new data, you have to collect for each observation all those 1,000 different features, all those 1,000 different characteristics or attributes for you can use for your model. And collecting more data is easier said than done. It can be an expensive process. And perhaps we want to train a simpler model that uses less features, such that when we want to use a model to make predictions, we have to probe less characteristics, less attributes of the observations. Instead of 1,000, maybe 5. Yes, we might lose some model performance, but it's going to be more easier to apply to deploy our model. So sometimes the goal isn't always just to generate the best model possible. We have to consider any external factors. When we work on a machine learning problem, it's very rarely does it exist in a bubble. What are some external factors that might influence our design of the things we do for picking our model and deciding how many features to use? There's a lot of feature selection tools in scikit-learn, which makes sense. In fact, let's go open up this link here. And here it talks about all the different ways we can select features, remove features from our data set. So we see a way we can remove features with low variance. There's also one called select k-best. We use this transformer when we're talking about scikit-learn. So select features according to the k highest scores. So the way it works, it says you have to pass it something else like a score function. It's going like perhaps correlation with the labels, and then it will select. Perhaps we can specify how many we want to keep. Let's say 4 features, so we'll only keep the 4 features with the highest correlation. So we need to pass what is this criteria, this score function, when we use something like select k-best. All right, let's play around with this one called RFECV. And as I always stress, when we use a new transform or a new estimator or a new model, let's go and look at the documentation to understand what's going on here. In this case, feature ranking with recursive feature elimination and cross-validation selected of the best number of features. So that's a mouthful there. But essentially what's going to happen is that it says, give me a model, give me an estimator. And what I'm going to do is if this estimator has a way to generate feature importance, then I'm going to take the full features, figure out which one was the least important, and drop it. And then retrain the model with that one less feature, see which one is the most important, which one was the least important feature, and drop that one. Hence recursive. So recursive feature elimination. It's applying cross-validation. And we can go ahead and use this model, and we can plot what is the R-squared value as a function of the number of features. So this might take a while here. So our data set, the California data set, has 8 features. So what happened there it did is that it ran the model and said, okay, it looks like this one was the least important. Let me drop it. Let me retrain the model with that drop feature. Which one's the least important? And drop that one. So it's also calculating the R-squared value. So we see here in this model, in this result here in this plot, is that as we decrease the number of features, the R-squared value increases, but at a certain point, it starts to drop. So at this point, we're losing some important features. So if we want a simpler model, it looks like we should go ahead and use anywhere from 4 to 6, 4 to 5. But anything less than that, we're going to lose some really important features, some features that really contribute to the predictive value, to predictive power of the model, so we shouldn't drop those. And now we have go ahead and have a simpler model and avoid problems like the curse of dimensionality.